Hello students, today in your geometry class you're going to be working on similarity in right triangles. So at the end of this lesson you should be able to calculate the geometric mean. So let's start with a couple of theorems and corollaries. Now Theorem 7.3 sets the altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original triangle and to each other. So I know that sounds a little complicated, but we're going to get to that on the next slide. Corollary 1.273 states that the length of the altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. Again, we'll get to that, but I want to make sure you guys see the technical definition for all these things. Corollary 2 states that the altitude to the hypotenuse of a right triangle separates the hypotenuse so that the length of each leg of the triangle is the geometric mean of the length of the adjacent hypotenuse segment and the length of the hypotenuse. So I know that sounds like a lot of words, but we're going to break that down in the next slide just to make sure we all understand. So, the geometric mean, as stated here, says proportions in which the means are equal occur frequently in geometry. For any two positive numbers a and b, the geometric mean of a and b is the positive number x, such that a divided by x equals x divided by b. So, here's the breakdown. What I decided to do is recreate these triangles for you. A right triangle, as denoted by the right angle at C. And what it does is, it says that when you have an altitude from the hypotenuse, or that extends to the hypotenuse like we do in blue, it says that it breaks down the triangle into two similar triangles, just like the one on the left and the one on the right. So, what that means is that we're able to find pieces of this triangle based off of what's called the geometric mean. And like mean means average. So, I broke this down and I color coded it to make this simpler. There's often going to be times where triangles are going to be cut just like the way this one is. And the way that we figure it out is by using the geometric mean. Now, your geometric mean in any right triangle is typically x, y, or z. It's always one of those three, the one that's connected to the right angle or the largest right angle, which in this case is at angle C. Now, the red one, which we've labeled x and colored red, if this serves as your geometric mean, what we want to do is make sure that we have a ratio, like such. Okay, now your fraction should always be fairly simple. I always like to look at it in terms of, here's a fraction, always starting off with the same exact stuff. Here's a fraction. Fix our lines really quick. Here's a fraction bar, here's another fraction bar, here's an equal sign in between. The way that geometric mean gets calculated is we have a geometric mean down here and a geometric mean over here. Now, the way that we look at this is to fill in the rest of the blanks. This is little side and big side. But you always want to start off with a geometric mean first. So let's start off with the red. We have our geometric mean, which is our x. So x and x are in the appropriate spot. So now let's look at our x. Now x is part of the larger triangle. So the smaller part of this triangle has to be A. Okay, and notice that the sides that are included in the geometric mean have to touch the geometric mean. So side length or segment A is touching x, so that's our little side. So I'll color that in green. So here's our little side. Our big side still has to be connected to x or touching x. So we have to use line segment AB, which is right here. And we're going to call that A plus B. Okay. Notice that y and z cannot count as a big side or little side because it is considered a geometric mean. So let's try the one in blue. Now for the blue, we have our geometric mean is y, and the little side that's touching our blue line is A, and our big side that's touching the blue line is B. And that's why we have the following geometric means below. So, I know it still might be a little fishy, but we're going to try a couple right now. Now sometimes in the book they'll give you two numbers and they'll ask you to find the geometric mean. If you were listening, you could use the following example that I put up, which I'm going to copy into this page. So, our geometric mean is the stuff that we don't know, which we have to calculate. So I'm going to take out our little side and call that 4. I'm going to take our big side out and call that 9. So now when we take the cross product of these things, we're left with gm squared equals 36. Then gm is equal to the square root of 36. So we know that our geometric mean is equal to 6. So that should be a fairly basic problem. Now we're going to do the same exact thing for example 2. Notice that our geometric mean here is going to be 6. So this we already know. So we're just going to fill in the blanks. Now the little side touching 6 is going to be 4. And the big side touching touching 6 is x. And notice the 4 and the x are interchangeable. So if you wanted to say it the other way around, that's fine also. So we'll take the cross product again. We get 4x equals 36. Divide by 4 to both sides. X equals 9. So that's how we solve for the geometric mean. Let's try two more just to make sure we have it down. Same exact formula as before. Notice I just keep copying and pasting it. The geometric mean here is x. So that's x. The little side is going to be 4 because that's the little side that's touching x. And the big side is not 21, but rather 25, which is 21 plus 4. So we take the cross product again, we get x squared equals 100, or 4 times 25, x squared equals 100, and x equals the square root of 100, which is 10. Last but not least, we have to solve for x, y, and z. So, however you want to look at this, we'll just choose y first as our geometric mean. So our geometric mean is y, y. Notice they try and trick here. The small side here is 6. The large side is not actually 30, but rather 30 minus 6, which is 24. So we take the cross product again, we get y squared equals 6 times 24. So 6 times 24. Y squared equals 144, and y is equal to 12. So we solve for 12. Now we have to solve for the other ones. So I'm going to move this along. I'm going to set up a whole new one. Geometric mean here we'll use as z. Small side here is 6. Large side this time is 30. So, cross product again equals 6 times 30. Z squared equals 180. Z equals the square root of 180. And last but not least, now we have to do the same exact thing for z, or I'm sorry, for y. So we're going to move that fraction along. Do this one last time. So small side, or the geometric mean is x this time, and the small side that's immediately touching the x is going to be 24, or 30 minus 6. And the large side is going to be 30. So, again, we take the cross product, x squared equals 24 times 30. X squared equals, see, that's 720. X is equal to the square root of 720. And that's all. Now it's your turn. Try these 3 problems. First person to post to Edmodo, everyone else will just reply. That's all for now. See you guys next time.